Hi, everybody. Thank you for joining. We're just going to give everyone a few minutes and then we'll get started.
Hi, Carly. Hi, JP.
Hi, Sarah. Okay, I think we can get started now. It's 3 o'clock. So I just want to say hello and welcome everyone to our Machine Learning and Chemistry Now and in the Future virtual event. We are happy to have JP here to lead our conversation on the future of machine learning, where he's presenting his exciting research and have the in-depth look at the ACS In Focus series ebook, Machine Learning and Chemistry. Before I start the introduction, I would like to remind everyone to use the Q&A function to ask your questions throughout the webinar. JP is a scientist applying state-of-the-art machine learning technique to a drug discovery task at AstraZeneca. Prior to this, he was a graduate student in the Chemical and Computational Engineering PhD program at MIT. Advised by Professors Heather Kulik and Yusuf Marzak, his research lies at the intersection of algorithmic simulation, machine learning, and optimization. With that, I will now hand it over to JP to start our discussions. Thank you.
All right, thanks very much, and thanks to everyone who's joining our conversation today. So, I guess I'll have a quick overview of how the talk's going to proceed. We're going to spend a little bit of time just on some introductory material and touch on a little bit about where machine learning and chemistry as a field is now, and where I predict there are going to be some growth areas for the immediate future. After that, we'll do a case study, one of my research projects from last year and the year before, and then we'll cover the In Focus ebook that Heather and I wrote and give a brief description of what that contains, and then we'll conclude. And between each section, we'll have a brief Q&A, so please ask your questions as we go. So just to begin with, I'd like to say that I think even today, machine learning and chemistry has achieved some pretty remarkable things, and the things that we're seeing in the last few years are, I would say, a step change from what we saw in the years and decades preceding that. So one example of this is this protein structure prediction competition that's been run every year for 10 or 15 years now, or every 2 years for every 10 or 15 years now. And something interesting happened at the 13th occurrence of this competition. So this is a competition where, based on the amino acid sequence of a protein, various people compete to predict the 3D structure of this protein. And so in 2018, a new team entered this competition for the first time, and they dominated the competition. They won 25 out of 43 of the unseen prediction tasks. And this is a really remarkable performance. But you can compare this to the next team. They're really a lot further ahead. But then in 2020, the next iteration of this competition, the same team really ran away with the show. And there's some quite strong reactions in the community. One of the founders of this competition said, in some sense, protein structure prediction is now solved. And that's quite a strong claim, but it shows you the sort of effect that this has had on this community. And that team, of course, is not a team of chemists. It's not a team of structural biologists. It's a team of machine learning scientists at Google at DeepMind. And here's a little prediction of their aggregate, so a little graph of their aggregate score across a few different years of the competition. And you can see that very little progress was made for many years. And then all of a sudden, when we've introduced these techniques, there's been a real step change in the capacity to predict new protein structures. And that's very exciting. This is just a brief schematic of how this model works. You know, it's a neural network that reads in the protein sequence, and it essentially predicts pairwise distances between each residue, and you can construct a protein out of this, out of the information that these models predict. And so this has led, you know, this Derek Lowe, who's a blogger in drug discovery, and I quite like this quote: "It's not machines who are going to replace chemists, it's the chemists who use machines that will replace those who don't." And I think that might be a little bit strong, but I think as scientists in chemistry, in any kind of chemical science domain, we generate data or interpret data all the time, and the techniques that fall under the umbrella of machine learning, I think, can be useful in almost any of these contexts. In a space a little bit closer to my work and my interests is this question of molecular optimization. So one of the great difficulties with chemical sciences is the number of possible molecules is unimaginably large. So this is a representation of all synthesized or imagined organic chemistry. It's sort of divided into this grid, and where we have colored regions, these are the areas of this chemical space that we've explored, or we formed those structures. And for example, some large database lives on one tiny island. So really only a tiny fraction of all the possible chemistry will ever be imagined by humans. And out there in this unknown wilderness are all of the future drugs, catalysts, solar cell materials, you name it. And it's a real challenge. I think anyone who works with chemistry will appreciate this. It's a real challenge to design new materials, to find new chemistry. And this is my interest in where I'm coming from and how ML can help solve these problems. So, you know, if we imagine a potential new material, this is a transition metal complex, the type of system I studied in my PhD, and we want to know some property about this new material. We have a few options in principle. We could synthesize and test this compound. We could physically make it, but that's expensive, and depending on what we're trying to make, it might be very complicated. We might not be able to make it, and anyway, it'll take a long time. An alternative is we could maybe do some type of simulation. So for example, with quantum chemistry or density functional theory, we might be able to estimate the properties of this material, and that might be faster if we believe that that calculation is accurate. But another option is we could predict this property in an empirical way. So if it's similar to some other molecule whose properties we know, we might be able to infer the properties of this material very rapidly. So now making predictions in seconds as opposed to hours or days. And this is the angle that my research has really taken. So, you know, if we take a step back for a second, there seems to be machine learning in every field. It seems to be growing all across sciences and across the consumer sphere as well. And I think it's good for us to wonder, you know, why is it so hyped up at the moment? Why does it seem like ML is taking over all these fields? And there's many reasons for this, but one reason that I think is part of it is it's a very transferable field. So if we sit here in chemical sciences, we can actually benefit from developments in, say, computer vision, another application domain for machine learning, for example, where convolutional neural nets were developed. And then we can take these technologies developed for understanding images of dogs and cats and apply them to help understand protein ligand binding poses, for example. There's still sort of pictures of ligand binding events. Another example that's very popular at the moment are transformers and natural language models. So these are sort of Google Translate or machine translation type models. These can be applied to, for example, map chemical reaction databases. So given strings that describe millions of reactions, this is a paper from IBM, you can build a model that can understand the way these reactions are related and predict the class of new reactions, for example. And it's not only a one-way field. So another technique that's been developed first applied to chemical sciences is actually graph convolutions or graph convolutional neural networks. And this technique has actually now been applied to all kinds of other applications. So we sort of have this cross-pollination between different scientific domains that trade ideas in some form through the kind of language of machine learning methods. So I think that is part of why we can have this really rapid growth across all all areas of science. So I was also asked to say a little bit about machine learning in the future, and obviously predicting the future is very difficult, but some developments that I think are really of a lot of interest are neural network potentials. So what a neural network potential is it's a machine learning model that basically tries to reproduce a force field, but trained on DFT data or density functional theory data from quantum chemistry. So this lets us simulate molecular motions, reactions, protein structure formation, all sorts of things at a high level of accuracy, but at very low cost. And this could be, really exciting. You could think of doing sort of a reactive molecular dynamics simulation on your laptop. So you could really do an atomistic simulation in much lower time. And you can see this is just some angle distance plots from the energy landscape of these models. And the one side is quantum mechanics, the one side is machine learning potentials, and they've gotten really good on some fairly complicated chemistries. Another area that attains a lot of interest, especially in the pharmaceutical industry, is that of synthesis prediction. So that, maybe given a target molecule over here, the machine learning model should predict how we would do this disconnect, and then how these reagents would actually be found in, say, a commercial database. So in this way, we are training machine learning models that can predict how we should do chemistry to build new target materials. And that's very exciting because it also, not only does it allow us to have suggestions for how to make things, but it also unlocks the door to sort of fully autonomous laboratories. So maybe the machine learning model can design a compound, but it can also design a way to make that compound. And then maybe it can tell a robot how to do that synthesis. And then you can have a fully autonomous chemistry platform. And there are a few groups who are very interested in those kind of technologies, which I think are really exciting. And then a final area that I think is heating up is 3D generation of molecules. So say in the last 5 years, we've been doing generative models, so machines imagining new chemistry, but mostly in 2D, either as a smile string or as a 2D graph. And we're now starting to see starting to see methods that handle 3D geometry start to emerge. And that I think is quite interesting because, of course, molecules are not 2D entities. There's 3D structured information. And so we're seeing technologies that can generate 3D conformers, but also that can understand 3D space a little bit more naturally. And I think those are an important growth direction for the field. So I think that basically summarizes my introduction. I think we can take a brief pause to answer some questions if we've accumulated some.
We did have a few. Someone had asked in slide 3, they wanted to know what you plotted against.
Let me have a look at, I'm guessing that's the map of chemical space. Yeah, so, this is, I didn't plot this, but it's a diversity plot. So these are a 2D abstraction of descriptors of the space. So I think if I remember in this paper correctly, they have 13 or maybe 20 properties of this chemistry of different molecules, and they've basically projected all the variance in that high dimensional space into 2D. So it could be a PCA. I think this is actually, excuse me, something called a self-organizing map, but it's basically a dimensionality reduction technique for a description of all of the space. So the idea here is points that are close together are somehow similar, and points that are far apart are less similar, but it's just a visualization of that, really.
What would be a good starting point for a purely synthetic organic chemistry lab to enter machine learning? Collaborations or simply learning on your own?
I mean, I think it's a really good question. I think I think both can be good options, and it's going to depend on your skills and interest. I think there's still scope for you as a synthetic chemistry lab to get involved in machine learning, doing it yourself, especially if you have some sort of niche application or some type of systems that you have a lot of knowledge about, because you can possibly transfer your domain knowledge to this problem. That said, I think there's a lot of good theory groups developing tools for machine learning for chemistry. And if you want to kind of buy into one of the ecosystems, it can be a pretty good way to get going quickly, especially if you want something standard like synthesis planning, for example. If you want to plan synthetic routes, I think that field is very advanced. And I would be tempted to reach out to someone who's doing it already to get a head start if you're coming kind of a priori. But if you're trying to do something, maybe predict yields for a certain class of reactions that your lab does, or something where you have some sort of unique data, then I think there's definitely still space for you to sort of do it yourself. because actually these methods aren't really complicated. Even the sophisticated models are generally, there's available free open source implementation. So you can just download a transformer from the internet and fiddle with it in Python for a few hours. And then, you can actually have a result. So the barrier to entry is not super high.
What role of machine learning on evaluation of magnetic field effects quantum level on molecules?
I don't think I've read anything about, well, I mean, okay, I should say something. My work is about spin splitting. So I've done a lot of stuff on spin state ordering of isolated transition metal complexes. So I'm not sure if that's the domain you're talking about, but if you're talking about sort of magnetic field predictions and things, there are some physics-based machine learning workflows, but I'm not aware of any for magnetism per se. That I could be unaware of that. It's just very far outside of my domain. Probably nowadays it's a safe bet someone has tried something like this, and if they haven't, they will soon. But.
Okay, great. I think we'll take one more question before we move on. If we think MedChem SAR progression as nonlinear, how well would you assess current ML approaches to solve nonlinear progression problem?
So I think one of the kind of frustrating things about, because now I'm working in a MedChem field, one of the frustrating things about it is SAR is actually really hard. You have this really kind of sensitivity to, you can have sort of one methyl group change completely inactivate a compound, and it's actually really hard for machine learning methods to solve these problems. So I would say in general, our ML understanding of SAR has not progressed very, very far at all, to be honest. You can take the most sophisticated methods that you can imagine, sort of multitask graph convolutional neural networks, and oftentimes they're only marginally better than ECFP, random forests, or standard cheminformatics tools. I think for this kind of thing, we have much more space to answer different types of problems. So either multitask prediction, so predicting multiple endpoints at once and doing it in sort of multi-parameter optimization sense, or maybe transferring information from project to project. So if we have SAR in one project that's maybe a kinase inhibitor, can we transfer that to another project? And I think that's where the wins are to be made. I think trying to just beat even standard cheminformatics workflows, I'm not convinced that we can do that really well. There's a few papers that make claims that you can do it a little bit better with the multitask graph convolutional neural networks, but they're not step changes like we see for protein structure prediction, for example. And there are many reasons for that, and I don't even think I don't know all the reasons for that. It's a very hard problem.
Okay, great. Do we want to move on to the case study?
Sure, yeah, I can talk about a case study. So this is, let me just start by saying this is a case study from my PhD. So we started this in 2019 about, it's just as I was finishing my PhD. But the idea was we were looking at redox flow batteries. So we were a lab that does primarily quantum chemistry on transition metal complexes. And one of the kind of application domains that we became interested in are these redox flow batteries. Now, these are a grid level energy storage technology. So, something that you might use to capture energy from wind turbines when it's not windy, or solar cells at night. Or it could also, they also have an advantage in that you can move the solvent that actually contains the dissolved electrolyte from place to place quite easily. So you might also drive redox flow batteries around in regular trucks, for example. So they can have some advantages. Essentially, they have the species involved in the redox reaction dissolved in solution, and then you can have a sort of arbitrarily large storage tank of electrolyte that you keep. And then you can also kind of size the reactive membrane independently of how much capacity you have. So you're not kind of limited in a solid state battery. You need a certain amount of membrane area, and that's also going to constrain how much storage time you have. In redox batteries, you can design these two variables independently. So they have some advantages. And transition metal complexes as redox couples for these systems have a few advantages. There's many other choices, but transition metal complexes have a few good things going for them. One is ionic stability. So they can accept and lose electrons many times without breaking down. they also have a good range of redox potentials available. So by manipulating the ligand field, we can move the redox potential of these materials up and down, and that might let us tune the battery's performance. One issue that they have is that they tend to have relatively poor solubility, or this is an aspect we'd like to improve. If we look at some equation that gives the energy delivered from one of these batteries, there's delta G solved here as the redox potential, so the actual change in gives free energy upon the redox process. But just as important is the concentration of the reactive species you can have at the surface, and these are just Faraday's constant and number of electrons per redox step. So, to solve this problem or to improve upon the state of the art, we need to design complexes that both have a targeted redox potential, but are also soluble. So we want to this is a way of thinking about a multi-objective optimization problem. We have these two different things that we want to control. And hopefully this work you'll be able to appreciate could be extended to different properties or different systems. It's really a methodology for solving multi-objective problems. So in order to set up this problem, the first step that we took was to design a search space. So design our chemical space where we would consider the solution to lie. And this is a large finite space. I'll show you how we constructed this. Looking at some existing ligands used for this sort of application, we decided that we observed most of them were sort of bicyclic heterocycles. So we considered various types of standard heterocycles. And we joined every possible combination of these together to make these sort of bidentate ligands. And then we also considered various decorations to these ligands in only in these positions, but you can imagine a variety of functional groups you might attach to these ligands. And as you start adding these layers of complexity, the size of the design space starts to explode very rapidly. And then by the time you start having a choice of different metals that you could pair these things with, we ended up with a design space of 3 million candidates that we sort of thought were reasonable choices that we wanted to investigate with our methods. So how do we go about picking which complexes we should study from this large design space? And that's really what we were doing. So I'll show you how we deal with that. So we might imagine we have this universe of different options to pick from. What we basically do is abstract these away into some chemical design space. So we know where each one of these points sits in the space. And then we take a few points to begin with, and we simulate those points using quantum chemistry. So in this case, density functional theory. But this is quite an expensive method, so we can't afford to simulate the 3 million complexes with DFT. So instead, we take these DFT results and we use them to parameterize a neural network surrogate model, which we can then evaluate in a fraction of a second. And then we can take this neural network model and we can make predictions on the whole 3 million compound space. And then we can basically use these model predictions to see where we should do our next DFT calculation. So, maybe this compound has good redox potential, this compound has good redox potential and is soluble, etc. But something we have to bear in mind when doing this is that the predictive power of the neural network is not uniform throughout the space. So if we try to make predictions on something that's very dissimilar to where we've investigated with density functional theory, we would have lower confidence in the model prediction in that region. So we want to do this in a kind of clever way, an optimal way if possible, where we incorporate both what we think the value will be and how trustworthy our machine learning predictions are based on the quantum chemistry that we've done. So firstly, I'll just show you that we can predict both of these properties with neural networks, with machine learning methods. So these are just parity plots. This is for redox potential. This is for, it's not actually log P because it's based on the solvation free energy, but something that we correlate with solubility. These are both quantum DFT derived values. And you can see we can predict these DFT values reasonably well. There's a test data that the model hasn't seen. And you can see we also have kind of uncertainty on each point. That's the confidence of the neural network. So, with these two models, we could screen our 3 million complexes, and it took about 3 minutes or 3.5 minutes on my desktop computer versus, maybe 50 GPU years to simulate these things with quantum chemistry. So that's a sort of major time savings that you can get with these sort of methods, and that lets you start to access much larger design spaces. With the way we make these predictions, we predict the value and then some uncertainty around it. So those are these error bars you can see on these points. And the width of the error bars depend on how far these points are away from our training data in a way in which we compute. So just for every prediction, we don't make a point prediction, but really we make a sort of uncertainty a sort of a range of predictions with a defined uncertainty. So it's Gaussian with respect to either direction. So we've got Gaussian marginals, but they don't have to be equal. So we might be, more or less confident about the solubility and more confident about the redox potential, etc. So all the points that we predict sort of have this multivariate Gaussian structure. And so I will explain a little bit about how we actually go about making these predictions and how we represent our complexes, just briefly. I mean, these are actually defined in their own papers, but the way in which we build our representation of this chemical space is we start at the metal center. So here's this sort of cartoon is the M here, and we look one bond away, and then we measure something about the atoms that you find one bond away. So maybe the nuclear charge. We actually do this for a whole lot of different atomic properties. I'm only showing it for nuclear charge Z, but you could imagine you could have a electronegativity, atomic radius, many things in this position. And you perform some kind of function. This is a product of these two properties, and you add them up. And that sort of gives you some information about the first shell. And then you can also look at the second shell and the third shell, etc. And you can actually consider not only products, you might also do subtractions or other operations on these pairs of numbers. And you do this for however many coordination shells you want, a correctly determined amount, and then you build up a representation, and you can use that to predict the properties of these compounds. This is actually like a graph theoretic representation. It's something like a graph convolutional, sort of like a graph convolution, but not exactly the technical discrepancies there. But anyway, you can take those values and you can make predictions either using neural networks or with kernel methods. So it's not sort of something that depends necessarily on deep learning. You can actually get fairly good results from SVR, random forests as well in this case. This is a methodology that we applied to many properties. So these are just some examples. This is spin state ordering of these compounds you can predict. Also frontier orbital properties. Here's a comparison. This is a linear method, lasso. It's actually a linear method. And then we have two non-linear methods here, kernel methods and a neural network, and you can see they actually perform equivalently, and that's fairly typical for this sort of data set size. Okay, so once we can map out our space with these descriptors, we end up with a picture like this. This is my picture now of a high dimensional space compressed into 2 dimensions, and this is just a principal component decomposition. And this is where these 3 million compounds live. Most of them are, or there's a color indicates how many compounds there are in each square. So there's a sort of concentration over here. If we looked at all the data we had when we began, so in our group, we actually kept a database of transition metal complexes that we'd simulated. We looked at this database. None of the points that we had simulated before were that representative of this design space. So in order to get started, we picked a diversity-oriented set of points to kickstart the process. So we did this sort of k-medoids clustering, pulled out some diverse starting points, simulate those. These are the training points that we saw earlier. Retrain our model so that it includes all of the data we have. And then we use a process called expected improvement, which I'll show you a little bit more on the next slide about, to pick which points to simulate again. And then we can use k-medoids clustering the second time if we wanted to down select how many points we should pick from those that are predicted to be useful. And then we can do this in a cycle. And after a few iterations, we start to exhaust the leading candidates in this space. So the way the 2D expected improvement works, I don't have much time to explain all of the details of it, but they're in this paper, and we can also talk about it in questions or even offline if you have any questions. But here are two properties: the redox potential and our surrogate for log D. There are 3 million dots on this graph. Each one is the probability of improving upon the current best design. So that's all of the probability mass of those two Gaussians. That's better than the Pareto front, better than the best designs that we currently have. And you can see that's fairly uniformly green. So these compounds are predicted to have a higher redox potential and potentially be more soluble than the best candidates that we had at this stage. The second plot is the expectation of that quantity. So in this case, you favor those points that improve by the largest amount. And that's why you get this non-equal coloring along the frontier. So you get these sort of hot regions that are yellow, and these are predicted to be the most impactful new complexes you could simulate. So this shows you the data that we started with. Because our predictions have uncertainty associated with them, there is a possibility that even if we predict the mean value for a compound is worse than our existing frontier, it still has a chance of being better than the best candidates we have. So that's exactly the Pareto front drawn on, and you can see in this long region here that correlates with where we have the highest expected improvement. So the algorithm thinks those are the most impactful complexes to simulate, with the optimal choice in a Bayesian sense. And this shows you the compounds that we then pick for our next round of simulation. And we then run this for a few generations. We're now going to watch a brief animation of that. So with every generation, we recalculate these properties. And so you'll note that the sort of predicted space changes shape as the model learns more and more about these systems. And it also moves toward the bottom right corner, which is where we are trying to drive the optimization to make highly soluble, high redox potential complexes, for example. And here you can see each time the points that we simulate for the next generation are highlighted. And eventually, the amount of gain that we expect to have, the probability that any compound will be better than our best set becomes negligible, and then we can terminate this algorithm when we no longer want to do any more simulations. So we did 5 generations in this particular work. Here's the same thing, just only DFT data. So here we have the initial compounds we simulated. That's our initial Pareto front. That's the second generation. So you see we have now the Pareto front moves to take into account these new points that we've added. And then we cycle through a few generations of this. Each time we move the Pareto front to the right and to the bottom of the screen as we find better designs. You'll see after 4 generations, something quite interesting starts to happen. We basically lose all confidence that we can exceed the redox potential. We've hit the sort of the limit of this finite design space. So we actually start to explore down the other axis of the Pareto front as well. And that's all an automated process. So an algorithm, from the beginning chose which compounds to simulate in a fully autonomous way, and actually submits and runs these calculations by itself. So this is a sort of fire and forget solution for optimizing in these spaces. These are just the convex hulls of these regions, so you can just see where they lie. So, I really do believe that methods like this, they provide a way of optimizing that's efficient. So hopefully we do few DFT calculations. In this chart, I have the properties that we sample in each generation compared to a randomly chosen set. So if you do a whole lot of random simulations, you get some good designs, but a lot of bad designs. So you waste a lot of CPU hours or GPU hours rather doing quantum chemistry on these compounds. Whereas if you follow these sort of guided principles, you can improve upon those. You can have a much more efficient sampling of the space. You can have only relatively few compounds per generation, and they're all fairly good. You can see after 4 generations, we stop being able to improve the redox potential. We actually still have some advances in solubility right down here. So yeah, basically what I said, we can identify the fruitful regions in these large design spaces rather quickly with few DFT evaluations. And I said this is I think a fairly general technique. People also do this for experimental systems, experimental design. So, you could view this as actually making and testing these compounds, or making and testing whatever it is that you're making and testing. Instead of doing a DFT simulation each time, you could guide your experiments in a machine learning assisted way in order to have to do fewer experiments while still getting good coverage of your design space. I'll also just say thanks to the Kulik group at MIT, who I worked in close collaboration with for this project, and that group is funded by a large number of partners who are responsible for the compute hours that we use pursuing these goals. Thank you. So I'll then take if there are any questions on the case study section.
Yes, here's our first question. What is the information?
I'm sorry, Carly, I can't hear you.
Oh, I'm sorry, can you hear me now? JP?
Oh, no.
Hello?
I hear you now.
Okay, I'm sorry about that.
No worries.
What is the information from DFT that you entered into the neural network? How did you probe the results?
So the information from DFT that we're using in this case is actually just the final value. So our representation that the neural network sees, how it sees the compound, is purely based on its structure. So it's those shell descriptors that I showed you. The DFT only goes into the endpoint, so the neural network learns to predict DFT final values. But there are a whole lot of exciting methods that actually use information straight from DFT in making these predictions. But the disadvantage of doing that, if you think about it, so you can actually make really nice predictions if you take some properties that you've calculated with DFT and use them as your description of the system. But then you have to do a DFT calculation for every new compound. So if you want to do a lot of if you want to sample a very big space, so you want to stay away from things that are derived based on quantum chemical inputs, because then you need to do the quantum chemistry before you make a prediction for each system. So,
let's see. What steps should we follow in other to generate a chemical space?
I think this is where you have to be the domain expert in your domain. So I think like a lot of the time you can think along the lines of sort of combinatorial chemistry. So now I'm in a drug discovery space. We think about amide couplings a lot. So, we have a list of acids and a list of amides that you could buy. That would be a good starting point because that defines some chemistry you can do fairly confidently, and you can get a large design space like that. But, your unique system is going to tell you it should be things you can make or simulate. So I didn't really get into the details given the time, but when we chose the metals to go in these systems, we made sure not to choose very heavy metals because you actually have difficulty simulating them with DFT. So you kind of are limited a little bit in the systems you can probe and study for whatever you're doing. So your design space should hopefully be as big as you can make it, but it should also be stuff that you can conceivably simulate or measure or study in some way.
Could the predictions of the best designed molecules be tested against actual synthesized molecules?
Yeah, absolutely. I mean, I would love someone to make one of these compounds and show me if I did well or badly in this case. It would be great. And I think with transition metal complexes, it's difficult because the synthesis tends to be quite involved and there has to really be motivation to do this. But certainly if you're talking about organic chemistry, we do this, it's actually done fairly standardly. If you're doing like predicting the outcome of amide couplings in industry, we'll check those predictions in practice. And sometimes they work, sometimes they don't. It depends on the problem and the system. Yeah, I think it is important to have a sort of simulation and machine learning and all this stuff is wonderful, but you actually at the end of the day have to make something and have to test and show that it works. I mean, that's what we ultimately want. We want to design a real material that you can make, and that's also why the construction of your design space is important, so that you really make compounds that you can access if you think this is a brilliant compound. So.
Do you estimate the log P using the DFT results as well? How is that done?
Yeah, so that, I mean, that's a very approximate, so as I kind of disclaimed this as a very approximate log D. It's actually just a free energy of solvation. So in a polar and non-polar solvent. So we just actually take it's just a free energy change. So it's not a super accurate measure for log P, no. We definitely agree. It's actually a very hard thing to estimate for these transition metal complexes. It's a very serious problem for the field of transition metal chemistry. So that is a difficulty. We're also constrained by what we can simulate in all these contexts. So hopefully it's better than nothing, but it's a relative free energy observation in two different solvents.
Could you elaborate on your approach for selecting a diverse initial exploration set?
Yeah, absolutely. So, I mean, that's actually a good thing to think about when you do anything like this, because you want to have, if I go back to just showing that, yeah, you see this is what it is. Basically, in this case, I use an approach called K-medoids clustering, which is really a way of clustering, so dividing the space in your descriptor space. So I have these descriptors that I'm going to use for prediction. They're these shell-based descriptors that I spoke about. We call them racks. You want to pick as diverse compounds in that space as possible. So you want to sort of divide that space up and to find out where all the compounds are, cluster them into similar compounds, and then take one representative compound from each of those. And so the technique here is we use called K-medoids, but you could use any clustering approach that you like. It can be hard to even judge how well clustering approaches are working. That's a separate approach, but there are some metrics you can test, silhouette distances and things, that you can use to see if your clustering is reasonable or not. Really, you want fairly good, you don't need to be perfect, but you just want something that you have made sure you've covered, the major corners of interest. You'll notice the points aren't on the very extremes of the space in any case, because we're trying to make sure that the average distance to the cluster centroid is quite low. So there's more compounds in the middle, that's why we got more samples there, and fewer compounds as we go out toward the extremes, because maybe an edge case is very unlike all your other cases, but that may not be that useful for model building because you can't necessarily infer that many more complexes properties based on these edge points. So.
Okay. How do you estimate uncertainty in predictions?
So it's another good question and another topic of a lot of research. what we do in this work is we actually use a distance-based uncertainty metric. So what that means is we measure how far the proposed compound is away from our existing compound, but we actually use the latent space of the neural network to estimate that distance. And actually, I'm going to have a slide on that in a little bit, and I'll try and remember to highlight this is exactly what we do. But we basically use the neural network to digest the whole design space, and then we take the geometry, how far away we're extrapolating from the latent space of that neural network. That's one approach that we found works quite well, especially for quantum chemistry data. But another popular approach is to take an ensemble of models. So you build multiple neural networks trained on either slightly different sets of the data or just initialize the training in a different way. And then you make a prediction on a new compound with all of these different models. And then depending on if all the predictions are similar, you have high confidence. If they're very dissimilar, you have low confidence. That's, I would say, the most common approach for estimating uncertainty in this field.
Okay, probably have enough time to take one or two more questions before we move on. How were the predictors for the machine learning model developed? Are these standard methods?
So actually, we developed these based on some existing standard methods, but we specialized them for our domain. So yeah, the full details are on this JChem paper, or JPhysChem paper. But essentially, we started with a family of graph-based descriptors, and we chose graph-based descriptors because well, actually, the first effort that we did in the space, it's not even on any of these papers, we used some single molecular properties and like what period the metal was in and what the atomic number of the connecting ligands were. And we found that these sort of very simple descriptors were lacking in something. So we wanted to move up a level of complexity to incorporate some information about molecular structure, and graph-based representations are really popular for this. You can get quite a long way using 2D graphs, the sort of abstraction of the molecule to its connected set of atoms. So we decided we want to try some graph methods, and then we actually adapted some techniques from organic chemistry to focus them more on the metal center, because transition metal chemistry has the sort of locality to it, especially when we're talking about something like the spin state ordering or the redox potential. Those are properties of the metal center, even though it's surrounded by ligands. So there's the sort of bias in the way the space is constructed that we consider everything as to how far away from the metal it is. And that's a reflection of how we view this problem, that these are the ligands that are perturbing the metal center. So it's a little bit specialized for this domain, and we used some domain knowledge in experimenting on that. But we also benchmarked it against standard approaches and found out it was pretty competitive. It was better than standard approaches for these systems. So some part of it is domain knowledge and some part of it is standard.
Okay, we'll have one more question. I feel that it is always difficult to convince other researchers that your prediction is sufficiently validated, especially when you have predicted something new. With no other methods available to validate, what is your suggestion on that?
Well, I mean, if you really have no other methods available to validate so I say, how I convince people about these predictions is I say, here are some systems that were predicted using these methods, and these are what the experimental values were, and this is how these methods correlate, even if they're historical. So for this redox paper, we dug out some measured redox couple redox potentials and investigated how well our methods could predict them, and found out that there was a reasonable correlation. So that's how you build a case. If you have no other model that can predict this property, then how are you going to convince someone? Well, the only answer I think is you'd have to have a physics-based model, so something like DFT, something that really incorporates physics that we believe and trust, but it's still going to be an uphill battle. I mean, I think that's a sort of teething problem for any predictive method, but it helps a lot if you have a sort of chain of logic, like DFT well describes this property, my neural network well predicts DFT, so therefore I trust this method. Also, with something like DFT, we can always do the calculation on the best predicted compound. So we don't have to predict 3 million compounds. We can just predict a few that the model likes. But then those values are sort of as validated as the DFT approach, or as validated as whatever computational approach you have. And then you're back to justifying that computational approach.
Okay, I think that's all the questions we can take at this moment.
Great. So let me just find out back to where we were. Right. Okay. So the machine learning and chemistry book. So this is this manuscript that we've put out with ACS in focus, and it's written by myself and Heather, my PhD advisor. I think I actually quite like this book. I mean, obviously, you expect me to say that, but I think we put a lot of thought into laying this out in a way that we think is approachable for people with training in chemical sciences. So I kind of struggled a little bit when I started working in this field because I needed to sort of get on board with how the machine learning methods worked. But for example, a lot of the books are written in terms of classification and image problems, image classification problems, and computer science applications, which I actually found quite interesting, but some people sort of can't really feel motivated to care about whether the image is a cat or a dog. So I would say this is it's a sort of intro to these methods that we've tried to digest through a lens of chemical sciences. So a lot of that, all the applications are different sort of chemical problems that we try and predict. The chapters of the book are sort of as follows. It begins with a chapter that Heather was the primary contributor for, that really looks at the history of machine learning in chemistry. And I think that's actually quite a nice perspective because people have been using neural networks to predict chemical properties since the 80s, possibly even earlier. There's some really, really early examples of doing this. So a lot of these ideas aren't new. And it's sort of understanding why they've come into so much focus in the last couple of years. It's a combination of factors. And then the content of the book, the sort of didactic content, the first chapter focuses on statistical learning methods, particularly for supervised learning. This is sort of like a theory of machine learning. Then we talk about linear and kernel methods as well as random forest. These are sort of like what we'd call shallow models. And then there's a chapter on representing chemical systems for machine learning. And then finally, we have a chapter on neural networks and representation learning. I'm going to say a little bit about these main chapters now, just to give you a flavor of what we put in there. It can be found interesting. And then finally, we have a list of just practical advice that we gained from forging out as a chemical engineering / theoretical chemistry lab into this field. I mean, we had a lot of help, but sort of the lessons that we learned along the way, what to try, what are sort of sensible defaults for all these things, and sort of how to get started. So first thing I want to talk about, and this is actually something that I find really, really interesting, it's this sort of theory of supervised learning. So how machine learning works and how we can expect it to work. So in a very general sense, we have some observations, so maybe a molecule or a particular structure, and it has some property. These could be its energy, it could be the 3D structure of the protein, it could be what reagents we use to make the synthesis happen. And so the way supervised learning works is we have some model families. So I'm going to fit, either a neural network or a random forest or some type of model. That model family defines many different possible models, usually infinitely many possible models. These are all different lines that have different slopes. And then the question is, how do you use the data you have to pick out of this model family the model that is going to best represent the relationship that you want to observe? So, which of these lines really represents the trends that I see in my data? And you can sort of abstract it away into the sort of idea of finding the parameters that define your model in its model family. But what's interesting about this to me is how do these models generalize? So, we don't want a model that can only predict its training data. So maybe I make 200 measurements and I can make a line that fits all those measurements perfectly. But how do I make a model that can predict new complexes? And of course, we sort of hinted on this already. It's not going to transfer infinitely far. If I build my model on small organic molecules and I try and predict a full protein property, it may or may not work. It may go quite catastrophically wrong, and how we can expect why that can happen or not. So as a simple sort of quantitative example, let's try and fit a function y equals sine 2 pi x with some noisy observations. So here's my gray line is sine 2 pi x, and the black dots are my measurements. I've measured them with some random noise, just as an example problem. Yeah. So what I see as a practitioner are these black dots. So I can start with a second order polynomial, just fit a quadratic function to this data. And as you might imagine, a quadratic function is not a really good description of a sine curve. It's only got turning points. So you have this sort of lousy fit. And you can see by eye here, this doesn't look like it's really going through my points. So let me try something else. What about a fourth order polynomial? So now I've added a little bit more flexibility to the model, and the fit is looking a little bit more reasonable. I'm still not touching all of my black points, but it's doing better than the second order. If I go up to an eighth order polynomial, now I'm fitting all of my points perfectly. So I'm perfectly interpolating the data that I have, But most of us would look at this red line and say, oh, I don't want that, because we say it's overfit. It's overfit to the training data. That's something that a lot of people have an instinctual idea about and a very rational fear about. Am I overfitting to the data that I have? So it's kind of important to put this on a rigorous pedestal and measure what we mean by overfitting. So we actually define two things in theory of statistical learning: the empirical risk, that's the error that we make on the training points. And then this other concept called the true risk, which is the error we make relative to the ground truth. Now, in practice, we don't know what the ground truth is, or if you're thinking about fitting DFT data, the ground truth is going and doing the DFT calculation for every compound, so you can't do that. But we can still reckon about how these work and learn from these kind of examples. So if I measure these two quantities, I have the analytic function here, so I can compute exactly what my error is as an integral. You'll see that the second order polynomial has high risk and empirical risk. So it's bad fit to the training and the test or out of sample data. The fourth order polynomial is a pretty good compromise. And the eighth order, while it has no empirical risk, i.e. it fits all of the training data perfectly, it has a very large true risk. So it doesn't fit the underlying function well. But this is a kind of complicated story, because if instead I had more points, so now I've kind of quadrupled the number of samples I have, now the eighth order polynomial is a better fit. So the sort of way in which you compromise about how complicated a model you have versus how much data you have is a really kind of subtle balance, and it's what we focus on in this chapter. So there's this rough idea in supervised learning that as you increase the model complexity, so you've got more polynomial orders or lower regularization, or however you reckon about model complexity, as you make the model more complicated, you'll be able to fit the training data, that's the blue curve, better and better and better and better. And when you get to a large neural network, you would expect that you'll be able to fit any training data perfectly. So, regardless of what your data is, how much noise it has, a neural network will be able to interpolate that data. But at some point along the line, our ability to generalize actually hits a minimum and then starts increasing. So this is everything from the right here is where the model has become overfit. So when we fit models in practice, we need to bear this in mind. And there are a few techniques, simple techniques that are actually used to determine where on this curve we are. These are things like cross-validation. And these are kind of what we handle in this chapter. So how we keep an eye on how we estimate the true risk of the models as we fit them. Then the next chapter of this book handles on shallow models. So it handles particularly about linear and non-linear models, but I will on non-linear kernels. It also treats random forest models and a few others, but I'll focus on the main idea being linear regression here. So you might imagine a 2D linear model. So I've got two descriptors that describe these points, and let's say I've measured 3 points, obviously in my contrived example. When it comes to predicting a new point x star as a function of these points, the way in which I make a prediction with a linear model is I see how far it is along each of the axes that I measure, and then I make some kind of prediction of this form. So some coefficient times the one axis, some coefficient times the other axis, maybe plus a constant if I have one. That's how a linear model works, and that's probably quite intuitive to most scientists and actually most people that you sort of correlate it with these descriptors. But the way in which a kernel method works, so this is in particular a Gaussian kernel, but there are variations of the theme, is to make a prediction on a new point, you actually measure the similarity of this new point to all of your training data. The way in which you measure that similarity is the kernel function. So in a Gaussian kernel, it's the square exponent of the negative square distance to your point. But in any case, the prediction of your value at x star is going to be a function of its kernel similarity to all of these points. But what is quite interesting, and what I didn't know until I sort of really looked into the theory of kernel methods, is actually linear models can also be represented as kernel methods. So you can actually write an exactly equivalent formulation of linear models as a linear kernel. And then there's a different way of defining similarity. It's actually the collinearity in this case. And this sort of very neat parallel is what we spend quite a bit of time on in this chapter. So we start from linear models and how they work and how you can sort of solve the normal equations and fit linear regression models, and then how they can be written in a kernel form. And then once you have this kernel form, it's a tremendously powerful thing because you can express many different types of regression in the language of kernel methods. And then you can have exactly the same implementation, exactly the same logic, exactly the same properties. You can sort of toggle between different types of model just by changing what this kernel term means. So what type of kernel you use. And so they're a really powerful class of methods that see a lot of use in chemistry. That's why we talk about them a little bit. The next chapter is about, I think I had a question about, how we represent our systems numerically, how we came up with this representation. And so this is a big task, and it doesn't have a single answer, and it's going to depend a lot on the type of system you're studying. There are some standard approaches, but in general, chemical space is discrete. Also, we have some different chemistries, each represented by one of these little dots. So these are, again, transition metal complexes. But what we need to do is to feed them into a machine learning model, which is a numerical model. We need to convert them into some sort of vector, some sort of numbers that represent these complexes. And the way in which we do this is with our featurization strategy is very important, because if we have two separate compounds and we look at both of their embeddings into the descriptor space, we're actually setting up our problem in terms of how far apart these complexes are in the feature space. So you can think about that in terms of the kernel model we just saw on the previous page, but it's sort of true in general. If your representation puts these two complexes very close together relative to others, you're sort of imparting knowledge, or you're encoding this idea that these two chemicals or these two molecules are similar. Whereas if you put them on opposite ends of the space, you're kind of doing the inverse. So this is really one of the areas where a lot of domain knowledge and your expertise as a chemical scientist can really come into play, because you have an understanding of the space on the left, and how you do that translation into the space on the right is actually where you can apply a lot of the sort of problem-specific information. Because once you have this representation, training any of the models that we mentioned are sort of routine model classes, are pretty fixed. But when we do this, we ideally want to think along a few different lines. We'd like to be able to do this quickly, this embedding process from molecule to numbers quickly and at scale, so we can tackle large problems. We want it to be as compact as possible, so we don't want to have a very large representation that's full of useless information, because then the machine learning model will be slower to train and have more work to do. And we wanted to encode our notion of chemical similarity. I'll also finally say this is sort of like quite a classic picture, if you like, of how feature engineering works in machine learning. What is popular nowadays is to use quite flexible representations and sort of let neural networks pick out the important bits for themselves, which we'll look a little bit toward the end as to how that works. But I think it's still a useful picture to have, because the way in which you represent your system is going to affect everything that you do downstream about it. So that's why in the case of my redox flow batteries, we had this representation that we built that encoded what we knew about how the quantum properties of the transition metal center are affected by the ligand shell. So in this case, even though these two compounds are actually to the eye quite different, you'll see that the first and second coordination shells are actually identical. So from a spin state ordering, these two complexes give you exactly the same spin state direction. So that's the sort of thing where our representation might place these complexes closer together, whereas if you were looking at just the size, say, you would put them maybe in different rooms of the house. Okay, so there are many different types of representation for chemical systems. There's some standard ones in every field. One that you may be familiar with if you come from any sort of drug discovery or cheminformatics background is fingerprints. So, these are sort of binarized representations of what chemical groups and structures are contained inside your molecule. So there's sort of pattern recognition about whether certain paths or fragments exist inside a given molecule. And these are actually really useful, and they often are surprisingly good at predicting molecular properties. They've got a long history in drug discovery as well, and they're obviously very cheap, because you just sort of check a molecule for whether it matches any of these binary inclusion flags, and you get the sort of long list of ones and zeros that describes the molecule. Sort of one step up in the complexity ladder are these sort of graph theoretic representations. So these are things that explicitly encode the connectivity between atoms. So these descriptors that I mentioned earlier fall into this class of methods because they represent the sort of full connectivity, what atom is connected to what atom throughout the whole system you're studying. But in the way we pose this, they don't have necessarily 3D information or a dependence on the specific conformer or anything like that. You just need to know what atom is connected to what other atom. And then as you move up this sort of hierarchy, you can also think about including 3D structure. So this now we have bonds and maybe the angles between atoms and these kind of things. And you can imagine that depending on what you're trying to predict, if you're trying to predict, say, the solubility of a molecule, for example, you might only care about kind of full molecular properties, so properties of the whole molecule, how many polar groups it has, where they are, you can probably get away with a graph theoretic or fingerprint-based method. But if you're trying to build a neural network potential, so a force field, a DFT quality force field, then you need to encode 3D information as well. And it can also be worth thinking about if your representation is on a per atom basis. So this is popular in neural network potentials, the sort of force field learning game, where you imagine each carbon atom is sort of experiencing a unique environment and some forces on that carbon atom as a result of its environment, what it's bonded to. And so you might want to actually represent your system not as molecules, but as atoms, whereas conversely, if you're trying to predict something that's a colligative property of a whole molecule, like maybe the solubility, it might make more sense to view it as a single, the whole molecule as a single entity, as I kind of discussed in the RFB work, but both approaches are commonly used. And we sort of review these a little bit in this chapter, but this is also a rapidly evolving field, so there's always new ideas coming out as we go. Then the final sort of chapter that I'm going to talk about here is the chapter about neural networks. And just to try and get a little bit of an understanding about how they work, in this book, we tried to provide a fairly comprehensive description, starting from the simplest possible unit, the neuron, how the actual building block of these models and how they can be coupled together to make sort of neural networks and how they're trained. But in sort of interest of time, I'm just going to keep it a very high level picture of what happens in these systems. But roughly, we start with our input molecule. So this lives in the feature space that we just described. So however you chose to convert your molecules to vectors, you have your training data or your training points, say, in this space. And then you can look at a little map of this. This is another sort of 2D projection of a high dimensional feature space. This one is called a T-SNE, but they're all basically just ways of drawing high dimensional spaces. So this is for that same RFB data that you saw. And here it's actually colored. So I've colored the space by the output property. So the red compounds, say, have high redox potential, and the blue compounds have low redox potential, say. And this is what the picture looks like using my derived similarity geometry, just as my descriptions give the values. And you can see that there are a few cases where they're like red and blue points right on top of each other. And there's definitely some blue regions and some red regions, but they're not very well separated. So what we do in a neural network is we pass this through a series of nonlinear transformations, depending on the depth of the neural network. So you might have a series of these nonlinear transformations, and each one of these little nonlinear transformations can be viewed as a kernel method. But we're sort of stacking a series of nonlinear transformations on top of each other. And then eventually we're going to predict the output property. But what happens if you look at the arrangement of points at this stage, i.e. before we predict the output property, then you can actually look at the latent space of the neural network. It's quite a striking difference, because what you can see is a lot of the kind of noise in the space has been smoothed out. So we've kind of flattened the space and put all of the molecules with a similar property on the one side and all of the molecules with a blue property on the right-hand side. And this is actually necessary because at the final stage of the neural network, it's just a linear model. So when we get to the stage, the property is actually just a linear function of where we are in the space. So for this regression to work, the neural network layers must arrange this kind of transformation that separates the points that you have by the output property. So you can kind of view it in a sense of like fixing the representation that you started with. Like if I had started with a brilliantly thought out description of these systems that looked like the right-hand side picture, then my linear model would be as good as my neural network. But of course, it's a high dimensional thing, and I don't know how to define these representations perfectly. And that's why we actually call this chapter neural networks and representation learning, because a lot of the time you can view these sort of deeper architectures as a sort of representation learning phase where we learn how to arrange the data and then some sort of predictive model at the end. And these things have lots of applications. You might have seen some generative models where we can sort of sample from the latent space directly and then convert each position in the latent space to a molecule. And that's sort of how generative models work in a very approximate sense. So that's just sort of a quick tease of how these neural networks work. And then you can think about measuring things in the feature space, or you can think about measuring things in the latent space. And that's actually how we calibrate the uncertainty estimation that we saw in the redox flow battery case study. So in this case, we don't trust the model to extrapolate very far in the latent space, whereas we are not so sensitive to feature space differences. And why that might be interesting is that the hope is the space has discarded the information that's irrelevant for making the prediction. So maybe there's some other functional groups in your system that are not affecting the redox potential. These are maybe not so important for its position in the latent space, but they might affect where it ends up in the feature space. But yeah, that's roughly how we did this. So then I'll just say, you know, a few quick words in conclusion before we move on to questions. I want to just say that, you know, I think it is becoming increasingly important to just be at least literate and aware of these techniques, because they're kind of creeping into all kinds of science domains. You really struggle to go to ACS and there'll probably be someone doing machine learning in some session that you're interested in. And even if the hype bubble, or when the hype bubble that we're in dies, because I think we should also be cognizant that we are in a very sort of in a hype cycle where everyone's very excited about machine learning, and it probably won't last, or at least you can't view it being quite as topical for so long. We'll find the new hotness will come eventually. But yeah, even when this lessens, I think these techniques and tools that we have developed and we've kind of put into production in many chemical systems will stay. So, you know, we're gonna keep doing these things for the foreseeable future, I believe. And I think it's important to say that everyone actually has a role to play in this kind of in this worldview. So this is a paper from quite a few years ago, and the title is Machine Learning That Matters. And it was basically a bunch of computer scientists who got together and said, well, you know, we can make these great progresses in benchmark tasks, so we can more accurately classify pictures, or we can beat the Go champion. You can play StarCraft, depending on your interest. But we can do all these great things, but how do we actually make an impact on the real world? And they basically divided it up into 3 parts. The sort of problem preparation part, which is just, you know, you phrase the problem in a way and you generate features, all these things. Then there's the actual, like the machine learning part, like the building the predictive model, validating it, making the predictions. But that's only gets you so far. You can sort of win a benchmark, machine learning benchmark, maybe if you're lucky. But it takes people who understand the actual system to deal with the output and to actually exploit what we get out of these systems. So it's still, you know, maybe Google can predict the protein structure for an unknown target, but it's still going to take, you know, a collaborative effort with someone who's, you know, maybe in drug discovery to think, is this a druggable target? Where can we act in this way? So I think there's a lot of space still for domain experts to interface with these tools, to benefit from them, and also to sort of impact their development so that we can solve more useful problems. So I think it's like, I get quite tired of papers that just say, oh, we've passed a little bit more on this benchmark. We made the QM9 prediction a little bit more accurate, because it's not really useful. So I think it's important to have input from people like you and me who have, you know, a knowledgeable about chemical science to see what areas we can improve and actually how we can benefit from these things that we've developed. So yeah, I think it's important that we try and, you know, not let this become a question of just benchmark winning, but actually a question of, can we make use of the methods that we develop? And then conversely, what are the openings in your field for machine learning? What problems do you want to solve? What data do you have? These kind of things, and how can we make good use of that? Thanks. And then that's basically all I wanted to say. So I welcome some more questions if we have them.
Great, thank you, JP. Yes, we are a little bit over, but I will ask you a few questions, and then we can wrap up. So what first steps do you recommend to those of us new to machine learning? Literature, software, etc.
I'm kind of a believer in learn by doing. So I would say start with like a very simple method, even just a linear model. I mean, if you're talking about specific software, it depends. You can do this in almost any software package. You can use Python, MATLAB, R, anything. But I think like get some data that either data you have or some publicly available data sets, and actually try stuff out, because you'll learn a lot by even just playing with it a little bit. I mean, there are obviously a lot of good resources you can follow, but I would say try and stick with a very simple type of model, like just try and train a multiple linear regression model to fit some data. There's a lot of learning you can do in noticing how that model works and how it extends. So I think, yeah, get started with something. There's publicly available data for a lot of different problems, a lot of different areas, and there's a lot of any software tool nowadays can more or less do this for you. So it's good to just get your hands dirty, I think, and try it out.
Great. And on a similar line, I'm wondering if you have any advice for creating generalizable models when you have minimal training and validation data.
I mean, this is very difficult. Typically, I would say if you have minimal data, you don't want to fit a super complicated model just because you're never going to be certain about how that behaves. So I think a good strategy for all problems is have good baselines. So try simple things before you try complicated things. And if you're going to have something complicated, it has to have a benefit that you can demonstrate over a simple thing. There is a whole lot of kind of exciting developments in machine learning around few-shot learning. So there are some people who try and really try and get the most out of minimal data. Something else I like for chemical sciences particularly is sort of the idea of transfer learning. So for example, for neural network potential, some really nice work Oli and ICF has done is basically you train the neural network potential on density functional theory data, and then with a limited amount of coupled cluster data. So you train, he has, I think, 20 million DFT points and a few 100,000 or maybe 10,000 coupled cluster points, which is a much more expensive simulation method. You can kind of hot start the model with the cheap data and then just fine tune it a little bit on the expensive data. So if you have some rare property that you only have 10 measurements for, maybe what you can find is a simple property that you have a lot of measurements for, and you might be able to have some sort of benefit from using a more abundant data source, even if it is a different property, as long as it's related.
Great. And since we're almost 10 after, I'll ask one last question. What is the risk of having a computer scientist with no or limited knowledge in chemistry applying his or her expertise in machine learning to chemical science?
I mean, they do that all the time. So I think, I would say don't, you talk about that as like a bad thing. I mean, in the one sense, it's nice that can benefit from the methods. I would say don't play that game. I wouldn't say try and, build a better image classification model or try and edge out some benefit on a benchmark, because you're basically, as I kind of described, it's the bit of the chemical knowledge just comes into is how you represent the problem and how you pose and interpret the data. How the actual model training works and what model type you choose and stuff, to some extent, that's really pure computer science, and there are a lot of very clever people working on these problems. So I think it depends on how you want to position what you do, but why do you want to compete on that? You have unique scientific knowledge. So I think finding ways to apply that is really how you can kind of have a niche and have something that you can really bring to the table. I mean, it's nothing stopping you becoming an expert in neural network training, but it's a whole separate domain to the experience that you probably have as someone who's sitting in this talk. So.
Great. And then I'm just going to
Stop sharing there.
Yeah, I'm just going to quickly share a slide for everybody, just showing that how to get access to machine learning and chemistry at access.acspubs.org/infocus. And what's coming up in the ACS in Focus series. In our collection 1, we have machine learning for drug development. And in collection 2, we'll have machine learning in materials chemistry and mathematics and machine learning. And so just want to say thank you for everyone for their time and for joining us today. And I have recorded all the questions that we did not get to, and we'll pass that over to JP to answer afterwards. So thank you and have a great day.
Thanks everyone. I really appreciate it. Thanks for the opportunity also, ACS. And yeah, have a good day.
You too. Thanks so much.
Bye.
Bye.